Hello there. Today we're going to look at section 3.1, exponential functions and their graphs. So let's first figure out what it means by an exponential function. Well, you have the function, and just any function, but the exponent is where your variable is. Let me zoom in there a little bit so we can get in a little bit closer. So the exponent is where your variable is. Okay, it's like this right here. For number 1, it says f of x is equal to 8 to the x power. So it says let's evaluate that using pi in there for x. So that would be f of x is equal to 8 to the pi power, which looks a little weird. But let me pull my calculator into the screen here. If I do that, I can type that in by saying 8 to the power of, and the pi is second in that caret button. The caret key that helps you get up there to the exponents. So you just hit enter, and that will tell you that is 687. It doesn't tell you where to round, so let's just round to the nearest tenth. 687.3. Okay? So these are just easy ones using your calculator. So let's come over here and do example number 2. So that'd be 8 to the negative 1/2 power when you plug that in. So if I were to do that, I would have, let's see here, clear that out, 8 to the, make sure you use the negative key, not the minus key, but to the 1 divided by 2 power, and that would give you the result of 0.35355. So let's round that again to the nearest tenth. That'd be 0.4. Okay, so that's the easy ones, just using your, let me just get the calculator off. That's just the ones using the calculator. Okay, now we're going to move on to example number 3. So we have, in the same coordinate plane, sketch the graph of each function. So let's start with f of x is equal to 3x. Since you've never graphed these before, I would say probably the easiest way to start it is let's just pick your x and our y. Pick your x and then solve it for y. So an easy number to plug in is 0, so that really means 3 to the 0 power. Remember, anything to the 0 power is always 1. So if I plug in 1, that'd be 3 to the first, which is really 3. If I went higher and higher, you can see obviously that we're going to get really big really quick, right? So let's go backwards a little bit. Negative 1, 3 to the negative 1. Hopefully you remember negative exponents. Excuse me. Negative exponents, all it does is does the reciprocal. So it'd be 1 over 3 to the first, which is 1 over 3. And negative 2 would be 3 to the negative 2 power, which would be 1 over 3 squared, which would be 9. Okay? So if I were to go over here and graph that, I would have 3 to, or the point 1, 0, the point 1, 3, 2, 9 goes way off the graph. The point negative 1 and 1/3, negative 2. Okay, what happens is we get really close to 0, but it never crosses. It just gets so close to 0. But 0 is what's going to be our asymptote there. Okay. Never can cross the 0, and it just shoots straight up there. Okay. A key factor is, remember, anything to the 0 power is always 1. So that's going to kind of be like our starting point for our parent function type thing there. Okay. It doesn't matter what this number is. That helps us figure out what that next number is there. But for at 0, it's always going to be 1, unless we're shifting it at all. So let's look at the other function. I'm going to get my other pen out here, my nice pink pen. So let's figure out what x and y is on this one. Okay. So if I plug in 0, again, 2 to the negative 0 power is just going to be 1. If I plug in 1, that really means 2 to the negative 1 power, which is 1 over 2 to the first, or just 1 over 2. If I plug in 2, that would be 2 to the negative 2, which would be 1 over 2 squared, which is 4. If I plug, then that's far enough going that way. Let's go back the other way. Let's plug in a negative 1. 2 to the negative negative 1, which would be really just 2 to the first, which is 2. If I plugged in a negative 2, 2 to the negative 2 would really just be 2 squared, which is 4. So again, remember, it always starts out at 0, 1. If I go over to 1, it's going to be at 1/2. If I go over to 2, it's going to be 1/4. But if I go backwards, a -1, it's going to be at 2. Negative 2 is going to be 1, 2, 3, 4. And it's going to go way up from that point. So that graph looks like something like that. Okay? So you can see those are the inverses of each other, kind of. Okay, with the exception of the 2 and the 3. But with the negative up top there, all that does is flips it over the y-axis. Okay? And keep in mind that anything to the 0 power is always 1, so that's kind of our starting base point for all these graphs. Okay, now we're going to go down to example number 4 and 5, the one-to-one property. Okay? When we have these things in equations, it can get could get kind of interesting here. Let me try to zoom in some more so we focus in on just those particular problems. So what we have is 2 to the x plus 2 power, because now our exponent has our variable in it, and that's where it gets a little more interesting. So than what your basic normal equation. You can't just divide by 2 because then that exponent is still up there. So what you got to do is get the bases on both sides to be the same. Right now our bases are 16 and 2. Well, can't really change the 2. I want to keep it there, but can we write 16 in terms of 2 to some power? Like 2 squared is 4, 2 cubed is 8, so 2 to the 4th is 16. Okay? Now, if the bases are the same, 2 and 2, that means the exponents are going to have to match up exactly too. So what you can do is kind of just ignore the bases at that point, and you know that x plus 2 has got to equal the 4. So you solve that hard equation there, and you get x equals 2. Okay, so that's all that is that you do. Let's go over here and do this one now. 1/3 to the x power is equal to 81. Now 1/3, remember with the negative exponent like we did up here, the negative exponent just flips that number around. So could I write that as 3 to the -1 exponent? Okay, and remember when you have a power to the power, you can really write that as just 3 to the negative x because you multiply those together. Okay, so we have that right now. Okay, so next we want to get the bases to match up. So 3 and 81. So 81 can go to, let's see, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81. So the bases match up now, so that's good. And now we can do the exponents have to match up, so negative x is equal to 4. So of course just divide both sides by -1 and you get x equals -4. And that's all that is to that type of problem. Okay, as we go on to the next page, we have graphing these things. Okay, so it says f of x equals 4 to the x. That's the parent function there that we're going to use. So it's already graphed in these problems for you. It says, and graph the new function. So we need to describe the transformation and then graph the new one. So remember when the number is inside with the x, like when we had before, like x minus 2 squared plus 4. The 2 inside went opposite directions, so that went to the right 2, and the number out back behind went up 4. Works the same way with these. If it's inside with the x or inside in there in the exponent, then it does the same thing, goes left and right. I'm going to zoom in here so we can see that really good. Okay, so that -2 means all it's going to do is shift it to the right 2, so it shifts to the right 2. Okay, so all we're going to do is take this graph. Remember 0, 1 is your first point, so it's just going to be shifted over to 2, 1, and then 1, 4 to the 1 power is there, but now we're going to go over here, so 4 to the first power is going to be 4 over here now. Still does not cross the x-axis because that's still our asymptote, and it goes something like that. Okay. Now remember, what does the negative out in front do to the graph? It reflects it over which axis? Reflects over the which axis? It would be the x-axis. If it's out in front, it flips it over the x. If it's inside with it, it flips it over the y. So instead of up here now, we're going to be down here. Instead of going over 1, 4, we're going to go over 1 and down 4. Still doesn't cross the x-axis, and it goes something like that. Okay? And going over to the last one there of this group here. Then we have a couple of transformations here. So we have 4 to the negative x plus 3. And remember, you always want to reflect it first and then do any shifting. So the negative out in front here reflected it over the x-axis, so this negative inside with the x is going to reflect it over the y-axis. And then we're going to shift it. The plus 3 in the back means it's going to go up 3. Okay? So reflect it over the y-axis, so it just flips like this. Okay? So the 0, 1 point doesn't get really shifted anywhere, or when it reflects it, but then it's going to be shifted up 1, 2, 3. Okay, the point 1, 4, which is normally on our graph, it gets shifted over to here. Let me move my pen there and shift it over to here because it gets reflected across the y-axis. And then we go up 3 from that point, so it'd be 1, 2, somewhere around here. Okay, now our asymptote was the x-axis, right? But when we shifted it up 3, our new asymptote is at the positive 3. So I like to kind of draw a dotted line in there. Remember, the dotted lines just help you with the graph so you don't screw them up. Don't really have to do the dotted lines, but that's what I like to do. And then, just so I know that when I'm graphing, I'm not going to go across that line, so I can get a pretty good graph there. Okay, now we're going to move on to the natural base e. Okay, you know how pi is a number, it's a special number because it's used a lot, and they, instead of writing out the whole number, 3.14 and blah 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 blah, they say it's pi. Okay, but it's a big, long, never-ending number. So e is somewhat the same type of thing. So the natural base e, the number e is called the natural base, and e is approximately this long number here, and it's one of those numbers that never ends. The function given by f of x is equal to e to the x is called the natural exponential function. Okay, and we're going to use this quite a bit in this chapter when we start doing logs and all that stuff. So number 9 says use your calculator. So let me zip my calculator back over here. It says use your calculator to solve for the given value of x in that function. So we really just have e to the 6.2. So it's really just taking that number there, that's 2.7 number, and taking it to the 6.2 power. So the good thing about your calculator is it can do it all for you. So if you notice that e to the x is that second and natural log button, it says you e to the 6.2 power, and that will tell you that is, let's round again to the nearest tenth, 492.7. Okay, let's get the calculator over, and now let's do the next one. So it'd be e to the negative 0.4. So clear this one out. E to the negative 0.4. Just a simple matter of just typing in a few buttons. And we get, again, round to the nearest tenth would be 0.7. Okay. And the last one here, scoot that over, and let's go ahead and clear that out. So we would have e to the negative 7.1, and that would be negative 7.1 would give you a total of, now, what does that mean there? Okay. E to the negative 4. What does that tell you? Well, that would be 8.25. Remember that e really means times 10 to the negative 4, right? So when you have a problem that comes out like this, obviously we can't round to the nearest tenth because then it would just be 0. So what you want to do is a couple different ways you can do it. You can just write it like that if you wanted to, or you could just move it over 4 times. 1, 2, 3, 4. So you'd want to add your zeros in there. So it'd be 0.00. I forgot a 0.008, something like that. Okay, and now on any test or quiz will always tell you where to round on these type of problems. Okay, now we're going to move on to number 12 and graph this function. So let's look at the f function, which is just the natural log of e. Let me zoom in a little bit there so we can get in a little bit closer. And again, I would suggest that when you're first starting with this, let's just pick an x. So that'd be e to the 0. Remember, anything to the 0 power is always 1. If I plug in 1, remember e is about 2.7, so that'd be e to the first, which is about 2.7. And if I plugged in a negative 1, that'd be 1 over e, which if you plugged it in your calculator, it comes out to be about 0.4. So if I come over here and graph that, that'd be there, 2.7 is about there, and negative 1, 0.4, a little less than a half. Okay, and this is treated very similar to just the exponential because it's the same thing, but just a special number there. I'm going to switch over to my pink pen for the g function. So we have 1/2. Remember, the number out in front is going to shrink it down vertically, and the x plus 1 is going to shift it to the left. So what happens is I'm just going to take this point right here, shift it to the left one, and it's going to go halfway up. So that'd be about right there. Okay. Take this point about 2.7 there, shift it over 1, back to the left. I'm going to go half of that. Half of 2.7 is about 1.35 or so. So that gets to about there. And so we get a function that looks very similar, but it's just going to be half of that. So it's going to be like that, and just half of it, half tall, and shifted to the one to the left. Okay, now we're going to move on to some real life examples here, and let's talk about money. So compound interest. Compound interest says after T years the balance A in an account with the principal P of an annual interest rate R in decimal form is given by the following formulas. Okay? If you remember, simple interest just makes interest on the money you put in there to begin with, and it's always just based on that original amount. But compound interest makes interest on the money after every month, so it makes money on your interest, on your interest, on your interest, like that. So the formula here is A is your principal amount, R is your interest rate, N is the number of times it's compounded annually. Like if it's semi-annually, it'd be twice. If it's quarterly, it'd be 4. Monthly, 12. Daily, 365. And then T is your number of years. Okay. If it's compounded continuously, and then it is PERT, principal times e to the RT power. So let's go down here and look and see what this means in this problem here. So on the day of the child's birth, a deposit of $25,000 is made in interest trust fund that pays 8.25% interest. Determine the balance in the account of the child's 40th birthday if the interest is compounded. These are 3 different amounts here. So let's start off by saying P is your 25,000. So I'm going to write down my different variables here. And I know my rate is 8.25. Now you want to make sure you put that in decimal form, which is 0.0825. And your T, your number of years you're putting in there, is 40. Now our N value is going to change each time we do this. Okay. For this problem right here, quarterly, that's 4 times a year, so our N is going to be 4. So all you do is plug it right into this formula that you have right here. That'd be A, which is your accumulated amount, that's which is what you're trying to find. Your principal amount, 25,000, times 1 plus 0.0825 over your N value, which is 4, times 4 to the 40th power. Now you can just plug that just straight into your calculator, and I'll show you one time how to do it on your calculator. Let me zip that over here. If I punch that in the calculator, I could just do it kind of like that. What I always do first is that I do the inside here first. I do the 0.0825 divided by 4 equals, then add 1 to that. And then I take that to that power, so I'm going to take that to the 40 times 4 times 40 power. That's that number, and then I'll multiply that times the 25,000. So I get my answer of the whopping $655,439, and since it's money, we're going to round to the nearest tenth. So if all you do is put in $25,000, 40 years later, if I do nothing to it, it turns into a nice $655,000. Not bad at all for not doing much work there. Okay, so let's see what happens if you compound it instead of quarterly, compound it monthly. So our end value is now going to be 12, and everything else stays the same, so it would be 25,000 1 plus 0.0825 divided by 12, 12 times 40. And when you do all that, I'll let you guys do that in your own calculator there, you come up with a grand total. Let's put dollar signs here. So if I do this, it's going to be $670,205.11. Okay, so it's a little bit more. Okay, it's a lot more to me. I mean, 15,000, that's quite a bit of money. And the only difference is, instead of compounding it quarterly, every 3 months, you're going to compound it every month. Now what happens if you just compound it all the time? That's when we have to use that other formula, PERT, is what I like to call it. Okay, P times E to the RT. So 25,000 times E to the R, which is 0.0825, times T, which is 40. Again, I'll just punch that straight in. Since it's a little bit different, I'll zip my calculator back over here. It would be 25,000 times E to the 0.0825 times 40, and you get a nice number of $677,815.97. Oops, let me scoot that over, sorry about that. You get that number right there, and that gets you your total. So the more often you compound it, the more money you're going to receive. Okay, so obviously that's better for you. So that will wrap this up for section 3.1.